All right, welcome back. In this lecture, we continue looking at examples of the use of characteristic roots and characteristic vectors to calculate functions and determine properties of the square symmetric matrix from which they were calculated. Now, in this lecture video, we're going to be looking at example 1.2. So let's take a look. So let cap sigma be the 2 by 2 matrix shown here. So the entries in the first row are 1 and 4, and the second row entries are 4 and 1. Now this is indeed a square symmetric matrix. The question we want to answer is it a valid covariance matrix? And so the first step in answering that question is to find lambda 1 and lambda 2, the characteristic roots of cap sigma. We'll then find the general form of the characteristic vectors of cap sigma corresponding to each of the characteristic roots lambda 1 and lambda 2. These characteristic vectors will be denoted by C1 and C2. We'll then verify that C1 and C2, which again are arbitrary characteristic vectors of cap sigma corresponding to its characteristic roots lambda 1 and lambda 2 respectively, will show that those vectors are orthogonal, and we do this by showing that their inner product, C1 prime times C2, is equal to 0. From C1 and C2, we'll find length 1 characteristic vectors of cap sigma corresponding to lambda 1 and lambda 2, and we'll call these length 1 characteristic vectors A1 and A2. We'll then verify that the trace of cap sigma is equal to the sum of its characteristic roots. We'll also show that the determinant of cap sigma is equal to the product of its characteristic roots. We'll then answer the following questions. Is cap sigma positive definite? Is cap sigma positive semi-definite? Is cap sigma non-negative? Once we've answered those questions, we'll be able to answer the question, is cap sigma a valid covariance matrix? And then we'll answer the question, could cap sigma be the covariance matrix of a multivariate normal distribution? If so, then we will define a two-dimensional random vector to have a multivariate normal distribution with this same covariance matrix, and we'll answer the following questions. We'll find the variance of x1, the variance of x2, the correlation of x1 and x2, and then finally, does a PDF exist for this distribution? So let's first find the characteristic roots of cap sigma. Now you'll recall that the characteristic equation of cap sigma is given by setting the characteristic polynomial of cap sigma equal to 0. The characteristic polynomial of cap sigma is equal to the determinant of the matrix cap sigma minus lambda times the identity matrix. Now cap sigma minus lambda times the 2 by 2 identity matrix is equal to the 2 by 2 matrix shown here, 1 minus lambda and 4 in the first row, and then 4 and 1 minus lambda in the second row. So we need to take the determinant of that 2 by 2 matrix. Now you'll recall that the determinant of a 2 by 2 matrix is given as shown here. So if we have a 2 by 2 matrix, the entries of which are denoted by A and B in the first row and C and D in the second row, then the determinant of that 2 by 2 matrix is equal to A times D minus C times B. That is, it's the product of the entries on the main diagonal minus the product of the entries off the diagonal. And so applying that formula to this 2 by 2 matrix, we see that the determinant of that 2 by 2 matrix is equal to 1 minus lambda quantity squared minus 4 squared. When we expand that and simplify, we get lambda squared minus 2 times lambda minus 15. And then we can factor that into the product lambda minus 5 times lambda plus 3. And so the characteristic equation of cap sigma is obtained by setting that characteristic polynomial equal to 0. Now the solutions of the characteristic equation are 5 and negative 3. And so the characteristic roots of cap sigma are therefore lambda 1 equal to 5 and lambda 2 equal to negative 3. Now you'll recall that the convention we use is that lambda 1 is always going to be the largest characteristic root, lambda 2 the next largest, and so forth. Okay, next let's find characteristic vectors of cap sigma. So let lambda be an arbitrary characteristic root of cap sigma. Then by definition, sigma times the vector c, where c has the two entries c1 and c2, must be equal to lambda times the vector c. And so when we perform that matrix multiplication, all right, we get the following system of two equations. The first equation says that c1 plus 4 times c2 is equal to lambda times c1, and the second equation says that 4 times c1 plus c2 is equal to lambda times c2. Now, subtracting 4 times the first equation from the second equation and then solving for c1 gives this equality. c1 equal to 15 plus lambda all over 4 times lambda times c2. So this is one equation with two unknowns, and therefore the characteristic equation has infinitely many solutions. This implies that there are an infinite number of characteristic vectors of the matrix cap sigma corresponding to this characteristic root lambda. Now let's let C2 be equal to T, an arbitrary non-zero real number. It follows that any vector C of the following form, C equal to the 2 by 1 vector, 15 plus lambda over 4 lambda in the first position, and 1 in the second row, times this arbitrary non-zero real number T, any vector of that form is a characteristic vector of cap sigma corresponding to this arbitrary characteristic root lambda. Now this formula can be used to find characteristic vectors of cap sigma corresponding to each of the particular characteristic roots lambda 1 and lambda 2. So let's find characteristic vectors of cap sigma corresponding to lambda 1 equal to 5. So using the formula on the previous slide, we see that any vector of the form C1 equal to, and then we're going to substitute 5 in for lambda in that previous, in the formula on the previous slide. And so in the 1, 1 position, we have 15 plus 5 over 4 times 5. And so we have 20 over 20, which is 1. In the 2, 1 position, we have 1 as well. And then we multiply that by t. So any vector of that form is a characteristic vector of cap sigma corresponding to the characteristic root lambda 1 equal to 5. Now, one such vector is obtained by setting t equal to 1. Doing that, we get a characteristic vector C1 equal to the vector containing 1 and 1. Now, let's verify our calculations thus far by showing that C1 is in fact a characteristic vector of cap sigma corresponding to the characteristic root lambda 1 equal to 5. To do this, we need to show that the definition is satisfied. That is, that cap sigma times C1 is equal to lambda 1 times C1. Now, performing the matrix multiplication, cap sigma times C1, we see that we get the 2 by 1 vector containing the entries 5 and 5. And if we factor out the constant 5, we have 5 times the 2 by 1 vector containing 1s, and that is lambda 1 times C1. And so we can see here that C1 satisfies the definition for being a characteristic vector of cap sigma corresponding to the characteristic root lambda 1 equal to 5. Note that the squared length of characteristic vector C1 is equal to 2. And since the squared length is equal to 2, the actual length is the square root of 2. Now, we typically like to work with characteristic vectors of length 1, and so let's find that now. So the characteristic vectors of cap sigma corresponding to the characteristic root lambda 1 equal to 5 have the following general form. C1 equal to the 2 by 1 matrix containing 1s times the constant t, or equivalently the 2 by 1 matrix with entries t in the first row and t in the second row. We can normalize this vector to get a characteristic vector of length 1. To be of length 1, you'll recall that it's necessary that the squared length of the vector be equal to 1 as well. In other words, the inner product of C1 with itself must be 1. So C1 prime times C1 must be 1. Now C1 prime times C1 is equal to 2 times t squared. That implies that the constant t must be equal to either positive 1 over the square root of 2 or negative 1 over the square root of 2. And so with that, length 1 characteristic vectors of cap sigma corresponding to the characteristic root lambda 1 equal to 5 are given as shown here. A1 is the 2 by 1 vector containing the entries 1 over the square root of 2 in both row 1 and row 2. We can also have the negative of that vector, which is in the opposite direction. We'll denote that negative A1. And so that's the 2 by 1 vector containing entries negative 1 over the square root of 2 in both the first and second rows. So each of those are length 1 characteristic vectors of cap sigma corresponding to the characteristic root lambda 1 equal to 5. Next, let's find the characteristic vectors of cap sigma corresponding to lambda 2 equal to negative 3. So any vector of the form C2, which we obtain by plugging negative 3 into the general formula for characteristic vectors for this matrix, are characteristic vectors of cap sigma corresponding to the characteristic root lambda 2 equal to negative 3. And so the general form here is the 2 by 1 matrix containing negative 1 and positive 1 in the first and second rows respectively, and then multiplying that by this arbitrary non-zero constant t. Or we could multiply the vector by t, and so we would have the 2 by 1 vector containing negative t in the first row and positive t in the second row. So any vector of this form, again, is a characteristic vector of cap sigma corresponding to the characteristic root lambda 2 equal to negative 3. Now, one such vector is obtained by setting t equal to 1. And when we do this, we get a version of C2, as shown here, that has negative 1 in the first row and 1 in the second row. Now again, I want to verify our calculations thus far by showing that C2 is in fact a characteristic vector of cap sigma corresponding to the characteristic root lambda 2 equal to negative 3. To do this, we will again show that the definition is satisfied. That is, that cap sigma times C2 is equal to lambda 2 times C2. And so performing the matrix multiplication, all right, cap sigma times C2, we get the 2 by 1 matrix with positive 3 in the first row and negative 3 in the second row. We can factor out a negative 3, And when we do that, we get negative 3 times the 2 by 1 matrix that has negative 1 in the first row and positive 1 in the second row. And that is indeed equal to lambda 2 times C2. And so we see that the definition is satisfied, and so C2 is a characteristic vector of cap sigma corresponding to lambda 2 equal to negative 3. Now, note that the squared length of this version of characteristic vector C2 is equal to 2. And so it follows that the length of C2 must be equal to the square root of 2. Let's find a length 1 version of C2. So to be of length 1, it's necessary that the squared length of C2 must be equal to 1 as well. And the squared length is equal to the inner product of C2 with itself, or C2 prime times C2, and that turns out to be 2 times t squared. This implies that t must be equal to either positive 1 over the square root of 2 or negative 1 over the square root of 2. So applying that value of t to the formula for C2, we get length 1 characteristic vectors of cap sig corresponding to the characteristic root lambda 2 equal to negative 3, as shown here. A2 is the 2 by 1 matrix with negative 1 over the square root of 2 in the first position and positive 1 over the square root of 2 in the second position. The vector in the opposite direction, denoted by negative A2, has positive 1 over the square root of negative 2 in the 1, 1 position, or the first row, and negative 1 over the square root of 2 in the second row. And so, putting all these results together in summary, the characteristic roots of this matrix cap sigma are lambda 1 equal to 5 and lambda 2 equal to negative 3. The length 1 characteristic vectors of cap sig corresponding to lambda 1 equal to 5 are shown here, a1 and negative a1. And the length 1 characteristic vectors of cap sig corresponding to lambda 2 equal to negative 3 are a2 and negative a2, as shown here in the slide. Next, we want to verify that C1 and C2 are orthogonal because they are characteristic vectors of cap sigma corresponding to different characteristic roots. And that's going to be the case. They will be orthogonal if and only if their inner product is equal to 0, and their inner product is C1 prime times C. So we see here that the inner product, C1 prime times C, is equal to negative t squared plus t squared, and so that is in fact equal to 0. And so because their inner product is equal to 0, this implies that the two vectors C1 and C2 are in fact orthogonal, as the theory tells us that they will be. Next, we're going to verify that the trace of cap sigma is equal to the sum of its characteristic roots, lambda 1 plus lambda 2. The diagonal entries in cap sigma are 1 and 1, and so the trace of cap sigma is equal to the sum of those two numbers, 1 plus 1, which is 2. The sum of the characteristic roots, 5 and negative 3, is 2, and so we see that in this case, again, the trace of cap sigma is equal to the sum of its characteristic roots. Next, we'll verify that the determinant of cap sigma is equal to the product of its characteristic roots. So the diagonal entries in cap sigma were 1 and 1, and the off-diagonal entries were 4 and 4. And again, you'll recall that the determinant of a 2 by 2 matrix is equal to the product of the diagonal entries minus the product of the off-diagonal entries. And so we have 1 times 1 minus 4 times 4. 1 minus 16, or negative 15. Now the product of the characteristic roots, lambda 1 times lambda 2, is 5 times negative 3, and that, of course, is negative 15. And so we verify that in this example, the determinant of cap sigma is equal to the product of its characteristic roots. Okay, next, we answer the following questions. Is cap sigma positive definite? The answer is no. Since one of its characteristic roots is negative, cap sigma is not positive definite. Is cap sigma positive semi-definite? Again, the answer is no. Since one of the characteristic roots of cap sigma is negative, cap sigma is not positive semi-definite. All right then, is cap sigma non-negative? Again, the answer is no. Because cap sigma is neither positive definite nor positive semi-definite, cap sigma is not a non-negative matrix. All right, is cap sigma a valid covariance matrix? No, it's not. Although cap sigma is a square symmetric matrix, it is not non-negative. Therefore, it cannot be the covariance matrix for any distribution. It's not a valid covariance matrix. And because it cannot be the covariance matrix for any distribution, we don't even bother looking at the questions that ask, could it be the covariance matrix of a multivariate normal distribution? Because the answer to that question is obviously no. All right, the next thing I want to do is to show how we could check whether cap sigma is non-negative using the definition of a non-negative matrix. And so let's let lowercase bold x, so that's a 2 by 1 vector with containing the variables x1 and x2. And note that the quadratic form given by x prime times cap sigma times x, when we do that calculation, it turns out to be equal to x1 squared plus 8 times x1 times x2 plus x2 squared. And so the question is cap sigma non-negative? Well, we already know that it's not. We know that it's not positive definite, nor is it positive semi-definite, and so it cannot be non-negative. Now, suppose that we were looking at this expression and we were using the definition to determine whether or not cap sigma was either positive definite or positive semi-definite. And if we had a hunch or a suspicion that maybe it was neither positive definite nor positive semi-definite, we might start looking for x vectors for which this quadratic form is negative. All right, that might be one of the first things we do just to see if we can find a counterexample to the definition to conclude very quickly that the matrix is not non-negative. Well, suppose that we let x be the 2 by 1 vector containing negative 1 and positive 1. All right, so we see that here. And so if x1 is negative 1 and x2 is equal to positive 1, then we see that the value of this quadratic form is equal to negative 6. And so we see that there does exist at least one non-zero x vector in two-dimensional Euclidean space for which this quadratic form is strictly less than 0. And that implies that cap sigma is neither positive definite nor positive semi-definite. And that would then imply that cap sigma is not non-negative. Now, this result is consistent with our conclusion regarding this question that was based on characteristic roots. You'll recall that in order to show that a matrix is not non-negative, really all we have to do is find an x vector, a non-zero x vector, for which the quadratic form is negative. Now, in some cases, it may be easy, as it was in this case, but in other situations, especially in higher dimensions, that could be fairly challenging. And so even though it can be easier to show that a matrix is non-negative using the definition than showing that a matrix is in fact non-negative, it's still easier to use characteristic roots for this purpose. So that's all we've got for this example. We'll look at another example in the next lecture video.